Hey folks, welcome back to another lesson, and we're now going to look at the photoelectric effect calculations. So we're going to define and use the words threshold frequency and work function, and then we're going to calculate calculations using energy, frequency and work function. So hopefully this will tie together some of the ideas we came across with the photoelectric experiment. So just to remind you, Planck said that light travels in tiny packets of energy called quanta, and that the energy of each quanta is given by its frequency. It's a fixed and specific amount, which you can calculate given by this equation E is equal to HF. Make sure you can find this equation in your relationship sheet. And let's look at how to apply this. So first of all, I want to introduce something called a threshold frequency, which is simply the threshold frequency F naught is the minimum frequency needed to release an electron. These are called photoelectrons, and this process is called photoemission. And the threshold frequency is unique to each type of metal. So please copy this down and notice you've got quite a lot of new terms there to remember. Things like threshold frequency, F naught, things like photoelectrons and photoemissions. So you can see from this diagram that these photoelectrons are only emitted if the light has a frequency greater or equal to the threshold frequency. Okay, so how can we represent this by a graph? Well, if we look at the energy of the electrons and the frequency, which is in hertz, now notice I've got kinetic energy because we're talking about electrons that are moving off. So at the threshold frequency, you've got just enough energy to release the electrons, but they're not actually moving off. So that's why it's the minimum energy. That's why it's called a threshold. As you hit the metal with a frequency greater than the threshold frequency, you start giving those electrons enough energy to be released from the metal, but also to move off the metal. And this is why they start getting kinetic energy. So this is a really nice simple graph, and notice it's a nice straight line. So there's a kind of a linear relationship there. So make sure you can marry this graph up with the photoelectric experiment. So increasing the radiance or amplitude of a wave below F naught will not result in any kinetic energy. So remember, it doesn't matter how bright the light we make or what type of light we use, if it's not the right frequency, we will get no effect. And so that's why for frequencies below the threshold frequency, there's nothing on that part of the graph. Okay, so the work function, another definition for you, so please copy this down as well. So the work function is called the minimum energy needed to release an electron is called the work function, and it's been given this letter W, capital W. It's calculated by H times F naught, where H is Planck's constant. And the work function is unique to each metal. Now be careful, because the work function is the minimum energy needed to release an electron. So that means it's just enough to make it loose so that if you give it any more energy, it can fly off the piece of metal. Okay, so to tie all of that together, to eject an electron, i.e. make it move, we need to give it more energy than the work function. And this extra energy is in the form of Ek and is calculated by the following equation. So Ek is equal to Hf minus W, where Ek is the kinetic energy in joules. Okay, nothing new there. W is the work function that is also in joules, and Hf is just the energy that's of the light ray, which is also in joules. Okay, now another way to write this equation is W is equal to Hf naught. So another way you might see this equation, and it might be a bit puzzling, is Ek is equal to Hf minus Hf naught. Okay, and you might look at that and say, well, isn't just the same thing subtract itself? And the answer is no, because the thing you've got to remember is that this is the minimum energy you need for the photoelectric effect to happen. So the minimum energy needed. Okay, sorry, my writing is a wee bit messy here. It's the minimum energy needed. And this one here is actually the energy from the light ray. So this is the energy from the light ray. So make sure you get this clear in your head. So let me just finish writing that. Energy from light ray. And I would like you to add this into your notes as well. Okay. Now, when I say light ray, I really mean radiation. So it doesn't have to be visible light. It could be gamma, X-rays, etc. Okay. So if we look at the equation, this is the kinetic energy, and the kinetic energy is given by the energy you supply through your radiation minus the work function, which is the minimum energy you need to get the electron to be removed from the metal. So that's why this equation makes sense. If you look at the work example later on, hopefully it will make a wee bit more sense. So now there is an experiment that we could do with this, so this is why I'm mentioning this, but you do have something called the stopping potential. So if we think about an experiment here, we've got a photocell and you've got incident light. And the idea is that when the light hits this photocell, it's enough, it's of the right frequency that it will eject the electrons, and the electrons move across this to the other side of the plate. And because you've got moving electrons, you've got moving charge. As you're moving charge, you then have an electric current. Now, that's quite handy, but usually what we try and do is once we've got this kind of photoelectric effect happening, i.e. we've got a current going through it, sometimes what we want to do is we want to apply a potential difference or a voltage across this to stop the electrons from moving across it. And we know we've stopped the electrons from moving across it because the current will reach zero. And that's what we call the stopping potential. So to summarize that, in the above experiment, if the potential difference is increased, it will eventually be high enough to stop the photoelectrons from leaving the photocell. And this is called the potential stopping voltage, and it means there will be no current read on this ammeter here. Vs allows us to calculate the maximum kinetic energy of the photoelectron. So we can use this to actually work out Planck's constant. And there's a very nice experiment I've got in class, but we won't talk more about that until we get back into class. Okay, applications of the photoelectric effect. Well, we use them in night vision goggles, cameras, CAT scans, and solar cells, etc. So let's look at some calculations first of all. So have a wee read of this question, and then we'll look at how to do some of the questions. And it's a past paper question as usual. So the first question is, ultraviolet light is shone onto the negatively charged metal plate. The gold leaf electroscope does not discharge. This indicates that the photoelectrons are not ejected from the surface of the metal. Suggests one reason why photoelectrons are not ejected from the surface of the metal. And you might sit there thinking, well, surely it should, because we know it definitely works for the ultraviolet light. But can you remember from last lesson that there's a really important thing you have to do with the zinc metal before we do the experiment? Okay, and the answer is the following. Okay, that first of all, it could be the frequency of the UV light is not high enough. Okay, or in other words, more technical terms, it's less than the threshold frequency. Okay, or the one that I was thinking of is that the plate might not be clean. So remember, one of the things you have to do before you do the experiment is you clean your zinc metal with an abrasive, sandpaper, to reveal the actual zinc metal. Okay, so that's worth 1 mark there. These other answers are also perfectly correct, but this is the one that I kind of taught you in the previous lesson. Okay, next one, it says the student adjusts the experiment so the gold leaf electroscope now discharges when ultraviolet light is shone onto the plate. The work function for the metal plate is this. State is what is meant by the work function. So again, it's a definition question. So the answer is it's the minimum energy required for photoelectrons to be emitted or ejected by photoemission. So notice how the last two questions were all kind of knowledge-based questions. Okay, final one. The radiance of the ultraviolet light on the metal plate is reduced by increasing the distance between the gold leaf electroscope and the ultraviolet light source. State what effect, if any, this has on the maximum kinetic energy of the photoelectrons ejected from the surface of the metal. Justify your answer. So we're really looking for two things. One, does it have an effect? And then can you justify what you said? So pause the video and have a wee go of it. I'll take you through the answer. Okay, hopefully you said that the answer was no, and the reason is because it doesn't matter what you do to the light, whether you increase the brightness or the the amount of light that's hitting it. The only thing that matters is whether or not the frequency is greater than the threshold frequency. So here's the model answer, okay? No change to the kinetic energy, as the radiance does not affect the energy of the photons. E is equal to hf is unchanged. So remember, I've been banging on about this, that irradiance has no effect on the actual photoelectric effect. It's whether or not the frequency of the light is greater than the threshold frequency. Okay, so the next question is, have a read of this yourself and have a go of it, and then I'll take you through the answer as usual. Okay, so it tells you the threshold frequency of the metal plate is 1.05 times 10 to the 15 hertz. So it's showing you on this graph here. It now says the metal plate is now replaced with a different metal plate made of aluminium. The aluminium has a threshold frequency of 0.99 times 10 to the 15 hertz. So how would the graph look like for the aluminium? So the answer would be, it'd be like this. Okay, it'd be much lower down because it's a smaller threshold frequency. However, you have to be careful. It's a lower starting frequency, but you have the same gradient. Okay, so make sure you don't get caught out by that. Lower threshold frequency, but the gradient is the same. Okay, so explain why the photoelectric effect provides evidence for the particle nature of light. So again, it's a wee one marker. And what we're looking for is that each photon contains a fixed or discrete amount of energy, or each photon removes one electron. But again, the one that I kind of taught you was this one here, is that it's packets of energy. It's a fixed amount. Okay, now let's try another question, because the more of these we do, the better you get at it. And this one is a calculation one. Okay, so have a read of this, and then I'll take you through the solution as always. Feel free to try it if you're confident, and we'll look at the solutions in the next slide. Okay, so let's look at the solutions on the following slide. So you can see, first of all, that you have the speed is equal frequency times wavelength, because we need to know what the frequency is before we calculate the energy. So remember, it's light, so the speed of it is always 3 times 10 to the 8 meters per second. We're given the wavelength, so from there we can get the frequency. Once we have the frequency, we know we can calculate the energy using E is equal to hf, so that's why we have Planck's constant, which is this value here, and then we plug in what we've got from the first part, and that gives us the energy in joules. Okay, notice it's a 4-mark question because you have to do this wee extra calculation at the front there. Okay, hopefully you didn't find that too difficult. If you're not sure, go over that again, folks. Okay, so how do we do the final part of this past paper question, which is determine the maximum kinetic energy of an electron released from the surface of the metal plate. And it's only worth 1 mark, but it's actually a calculation question. So the calculation we're doing is using this equation here. Kinetic energy is equal to the energy supplied by the radiation minus the work function. Okay, so obviously it's quite tricky to see this because I've put them all on different slides, but the information that we've got so far is the following. We've got that the energy from the radiation is 3.79 times 10 to 19 joules, which is what we worked out in the previous question. And then we're told in the actual question that the work function is 2.24 times 10 to negative 19 joules. So notice again how they're sort of guiding you through the question by getting to work out the energy supplied in this experiment, and they're telling you what the work function is. So from there, it's pretty straightforward. We write down our equation as usual, and then we sub in for our values. So this is the energy supplied, this is the work function, we subtract them, and then that gives us the kinetic energy of the actual electrons. And if we wanted to extend it further, we know what the mass of an electron is. If we know the kinetic energy, we could then work out the speed of these electrons emitted. And that's your final and second worked example there.